In this video, we will talk about L network impedance matching. To give you an idea of the impedance matching in general and L network in particular, let's consider this load ZL, which is driven by some source on the left hand side. And this load ZL could be something like an antenna, and it's not necessary that load ZL is always terminated into a desired impedance. For example, let's consider the source that is driving is as a 50 ohm resistor. That means we have a 50 ohm resistor looking from here. In order that this 50 ohm source impedance to match to a load, the load value must be 50 ohm for a maximum power transfer. If you have not seen my maximum power theorem video, please go and check that. There are two rules. Number one, if you have only a resistive load, there is no reactive element to it, then this 50 ohm resistor impedance should be matched to the 50 ohm resistor. But if you have a reactive load, for example, what is the meaning of a reactive load is that this load ZL will be a number something like 20 plus 60J. For example, this will be an inductive load because this impedance, the reactive element will be J times of 2 pi omega L, and therefore this will not match to this source. So in order for the source and the load to match for the maximum power transfer, this load must be complex conjugate of the source impedance. So if the source impedance is 50, then the load impedance should also see a 50 ohm resistor. So what do I do here in order that this source looking into here sees a 50 ohm resistor? What we do is what we call as an impedance matching network. So we insert a black box, and that black box I will call a matching network. And in this particular, the L network matching has a special simplified matching which uses only just two elements, and both of these two elements must be a reactive element, because if we introduce the resistor into it, then there will be power wastage on that resistance. Because anytime you introduce a resistor, then any current flowing through it will have an ohmic drop, IR drop, that will be lost. If you have a reactive element, that instantaneous power, there will be an instantaneous power drop. But if you look at the average cycle, one complete cycle, either a capacitor or an inductor, then over a cycle of this, there is net power drop is zero. So for example, in a capacitor, it charges in one half cycle. In the later half cycle, the charge capacitor on the charge capacitance on the capacitor, that drives back the power. So in a complete cycle, the power loss in a reactive element, an inductor or a capacitor, is zero. So with this information, what we do is the matching network. There are two types of L network matching network. In one in which we introduce this element here, an element here, and the second element over here. And both of these elements are reactive elements. Now, it is not necessary. You can ask a question that why only 50 ohm source? In general, the impedance, the source driving this could be other than 50, including a complex source. For example, this could be 20 plus 40J, but we are making a simplified assumption that our source is 50 ohm, or we will, for simplified thing, we call Z0. This can be achieved, for example, if we do not have a, let us say, a source which is not a Z0, for example, it is 20 plus 30J, we can add a matching network here. I will call it matching network. and then this matching network will eventually transform it to the Z0 impedance, and then we have a coaxial cable, could be a long coaxial cable going right from this matched network to the our load, and just before the load we introduce another matching network. So this is how it is done in real circuits. So it's not, without losing too much into generality, we are introducing the assumption that our source that is driving this whole circuit has an impedance of Z0, and we need to introduce this matching network so that after we introduce it, and if we look into it, all we should see is Z0. That is the equivalent impedance of these three networks is Z0. There is another type of the matching network which is done by imputing a series element first closer to the Z0 and then a shunt element. Both of them are called L network impedance matching networks, because this is looking like an L here or an inverted L here, and both of these networks are simple to design and they are very precise for a given frequency. We will first derive what these values of these elements are, and for this we denote this element as Jx and this element as Jb. Jx is the complex impedance of this element. For example, if this is only an inductor, then this inductor's X can be found by at a given frequency as 2 pi f into L. Because these elements are frequency dependent, so this matching network will work at only one given frequency. And what happens after the frequency is out of f, we will investigate it later. And in the same way, for example, if X is a capacitor, then this will become X will become 1 upon 2 pi f into C, and into J. We can also write J here, so this will become minus of this whole thing times of I of J. This is a complex number. If this is a capacitance, this whole X number will be a negative number. Same thing happens for this element. Because this is a parallel element, this JB is the total admittance of this element, and this is the total impedance of this element. And the reason we use a admittance here is because it's in parallel, so it's easier to work. It's easier to work with admittance when something is in parallel with another impedance network. So let's try to derive the values of B and X here. So for that, we notice that if we combine these two, ZL, and I write ZL as RL plus J times of XL, the equivalent impedance of this and this can be found by, let us call it Z1 equal to that. If JB is admittance, so its impedance will be 1 upon J times of B. An equivalent impedance of JB and RJ plus JL will be equal to 1 upon JB multiplied by RL plus J times of XL divided by sum of these impedances, 1 upon JBL, 1 upon JB plus RL plus JXL, which means that we are now looking at a network composed of JX and Z1, where Z1 is the equivalent impedance of these two elements. Now, in order that this whole thing, from looking from here, should have an equivalent impedance that should look resistive, we must have the imaginary part of the Z1 equal to minus Jx, because eventually we are going to add these to Jx plus Z1. But the second most important thing that should happen is that the resistive part of Z1 should be equal to Z1, because here it is the place we can determine the net resistive part of this. Once we have found this equivalent impedance, we have no control over the resistive part, because this is then going to change only the reactive part. So the condition is that the real part of Z1 must be equal to Z0. So to do that, let's simplify this further. This I can write it as RL plus J times of XL divided by, I write it in such a way that the real and imaginary parts are separated. So I will write 1 minus B into XL, and the imaginary part is J RL into B. And to simplify it, to separate the real and the imaginary part, I multiply numerator and the denominator with this much minus this. So this becomes RL plus J times of XL multiplied by 1 minus BXL, and I will write it as minus J RL into B divided by this thing 1 minus BXL plus JRLBL multiplied by this minus this will become this square plus this square. 1 minus XL into B whole square plus RL square B square. And this I can simplify it. In this numerator, I am going to separate the real and the imaginary part. So that way I will get a real term and an imaginary term, and then we can apply the condition that we just discussed. So I can write RL minus RL B XL, and then another real term comes from by multiplying this term with this, which will be plus XL RL B, and then this is our real term, and then the imaginary term will be plus JXL. So I write XL here, and then I write XL minus BXL square, and then another imaginary terms comes from by multiplying this term with this term, which is minus RL square B. And the whole thing divided by 1 minus XL B whole square plus RL square B square. And this term, these two terms cancel out to simplify our, and this is multiplied by J. So this is our RL divided by, I can simplify it a little bit by expanding this term. I get RL square plus BL square, RL square plus XL square B square minus 2XLB plus 1, and then we have the term here XL minus, I can write it XL minus XL square plus RL square into B times of J. This is our expression of the equivalent impedance Z1. Now the condition that the real part becomes Z0 is that the real part of Z1 must be equal to Z0, which means that this RL divided by RL square plus XL square B square minus 2XL into B plus 1 must be equal to Z0. That is the condition that our real part is of this Z1 is Z0, because that is the part Z0 when you add it with Jx in series will give you a real part, and that must be equal to Z0. So we can simplify this to if you take all these things here, it will become, we can reduce it to a quadratic equation in B. So we will get RL square plus XL square multiplied by B square minus 2XL into Z0 B plus Z0 minus RL. This thing must be equal to 0. This is a quadratic equation in B, which we can solve for B using B is equal to minus B 2XL Z0 plus minus square root of B square, which is 4XL square Z0 square minus 4RL square plus XL square multiplied by Z0 minus RL divided by 2 into RL square plus XL square. This is what we have now. A little bit of math, but not, hopefully not too generous. We'll get 2 cancel, and there are 4 here, so they also get cancelled. One mistake here, we had a Z0 multiplied by here, so that had become Z0 here, and then 2XL into Z0, the rest should be, this is a Z0 term here, 2 gets cancelled, and we get, and let's divide it by Z0 here, we get XL plus minus square root of XL square Z0 square minus RL square. Okay, and because of this Z0 here, we have a Z0 term here, minus RL square Z0 square, and then RL square into RL, that becomes plus RL cube Z0 minus XL square Z0 square, and then plus XL square RL Z0, and then divided by, I put 1 upon Z here as I divided it by the Z0, divided by RL square plus XL square. This RL square, XL square Z0 cancels with this XL square Z0. We have slightly simplified expression. Remove this whole thing. I get B. I should have kept the part before that, but let's see. We'll get B is equal to XL plus my B equal to XL plus minus 1 upon Z0 square root of RL square, and I will take minus RL square Z0 plus RL cube Z0 square cube Z0 plus XL square RL Z0 divided by RL square plus XL square. If you simplify it a little bit, you will get XL plus minus, you take Z0 common from here and also take an RL common here, and this becomes square root of RL divided by Z0. You take Z0 common, square root G0, this becomes cancelled with this, you get Z0 here, and this is square root of R and Z, this becomes RL square plus XL square minus R naught Z naught divided by RL square plus XL square. That is the expression for B naught which we can use for our calculation. I'm trying to make sure this equation is matching with the result that I have here, which it looks like. So we have this is the condition for JB, and if you remember, if you can go back to the equation, we had an expression for Z1 which has some terms here and another term times of J divided by something like this here. That was our expression for Z1. So the next step to do is, we got B, we take this imaginary part of this equation Z1. Let's derive it quickly because we have done so far. I will do, because I removed this, we will have to write it again, but I would like to go through all the steps, make sure we are doing this. So to quickly, we had given Z1 is equal to 1 upon JB into RL plus JXL divided by 1 upon JB plus RL plus JXL, and this we had gotten RL plus JXL divided by 1 minus XL into B plus JRL into B, and this whole thing multiplied by this complex conjugate multiplied over here, 1 minus XL into B plus minus JRL into B, and that gave us RL, and this thing 1 minus XL into B minus JRL into B, and that gave us RL. These terms are cancelled out. RL and XLB and JXL, XLRLB and XLRLB cancelled out, and we had plus J times of XL minus XL square B minus RL square B divided by 1 minus XLB whole square plus RL square B square. Now this imaginary term, this whole imaginary term must be equal to the complex conjugate of Jx. So if we have, let a term Z1 something like Z0 minus Jx, if by some magic we could get Z1 value like this, then this Z1 and this Jx are in series, and if I add these two, I get an equivalent impedance of Z0, which is the condition for the maximum power transfer. So the first condition we applied and got the value of B. We will apply the second condition and we will get, which means that this whole section here must be equal to minus X. So we can rightly apply this thing minus X here, and then we can substitute the value of B that we obtained here in this equation. There is one trick though, that you will find is that this whole term, because we have RL here, now we know that we have found RL upon this much is equal to Z0. Okay, so this term I can write it as RL divided by Z0. So the condition becomes J times of XL minus XL square into B minus RL square into B divided by, this whole term can be written as RL divided by Z0. RL divided by Z0 from the above condition here. That will be equal to minus X. And from here we can simplify and substitute the value of B here. Let's do a little bit more just to make sure we are getting close. So XL minus XL square plus RL square into B, that will be equal to minus x RL divided by Z naught, and B into RL square plus XL square is this much, and then from there we can take XL. If you simplify whole thing, you should get X that is equal to, I'll directly write it to you so you can do this equation, you can verify it. X is equal to B Z naught XL square plus RL square minus XL Z naught divided by RL. We are very close. Just to make sure, you take this term to the, take this XL to the other side, and then just do some simplification. If there are some mathematical mistakes, you can figure it out. But eventually what is happening is, we would like to discuss those results, how to proceed from here to actually design the things. Once you have found the value of, before we go on, the condition that that we derived is that B has to be a reactive element. What does that mean? That means that B must be real. B cannot be imaginary, because if B is imaginary, then its multiplication with J will give us a real element. And to be real, this whole thing under the square root cannot be negative, which means the condition is RL square plus XL square minus R naught Z naught. This must be greater than or equal to 0. This must be non-negative number. If this condition is met, then we can design and find the value of B here. So let's say we get the value of B as something like 30, and we get the value of X something like 40. B can be negative and B can be positive. So let us say we got the value of B as positive, which means J times of X must be 30. Which means that this B has to be, and finally you will see that once you solve this equation, you will get two values of B. One could be positive and another will be negative. Okay, so from the positive value of B, you will get a inductor and capacitor network, because when B is positive, then when B is positive, which means that this is admittance, that means 1 upon JB is positive, which means its impedance is equal to negative. And so let's write it. B positive means JB is, this means 1 upon JB is equal to negative. That means it is a capacitance. So in that case, if B is positive, we must have a capacitor here, and that means that we must have a inductor here. On the other hand, if B is negative, that means 1 upon JB, which will convert J into a negative thing, will become positive, and in that case, we will have a inductive and a capacitive network as our. So once you solve these things, you will get two values of this, and from these two values, we will get two types of the L network. Let's continue. We are not finished yet. What we need to consider is, let's say what happens. But before I move on, I wanted to tell a few things. That what does that mean? Let's say we get a value of B as 40. What does that mean? It means that JB is equal to 40J, which means that we will usually get the value of B as something very less number, 0.02 for real network, which means I will keep it at 0.01. So that means JB will be equal to 10J, which means that the impedance of this whole thing, let us call it ZP, will be equal to 1 upon JB, which will be 1 upon 0.01, which will be equal to, I'll keep it 0.1, 0.1, which means this is equal to 1 upon 0.1j, which will be minus 10j. If you take multiply numerator and denominator by j, you get minus 10j, which means that this has an impedance of 10j, and that has to be a capacitor, which means 1 upon 2 pi f into c will be equal to 10. From here you will get the value of the capacitance as 2 pi f into 10, this much of 1 upon 2 pi f into 10, this much of farad. So this value, with this value we get that the whole thing matches for one particular value of f. That means our matching network will work only for one particular value of f. So we have ZL is equal to Z0, this Z0 for x, for f is equal to some frequency f0. But what happens when f is, let us say f0 plus some delta p f, or f0 equal to f0 minus some frequency delta f? ZL will have some component Z0 plus something, and this case is Z0 minus something, some variation from Z0, which means that the moment you go away from f, this network is no longer matched. That means the power is not be optimally transferred. So your output waveform will look something like this, and this curve will be very sharp because of this nature of this matching network, which also means that there is no possibility, or we have no control over expanding the bandwidth of this curve. So how do we expand the bandwidth of this network? And for this we have the concept of the pi network. What we do here is, instead of two element, we add another element like here. And if I add another element here, then I can play around with those three values, and then I can shrink or expand this curve. In other words, we have a control over the bandwidth of this curve. So this will be the topic of maybe the topic of my next lecture. But before I finish this lecture, I wanted to give you another variation of this matching network, another that we started. We could instead start with a series element here and then a shunt element here. Let's call it JX and let's call it JB. And the equivalent impedance of this network looking from here must be equal to Z0. What does that mean? That means if I take ZL and ZX, that will have some impedance, and from here, from these two, we will get a result which should have this RL element, the resistive element must be equal to Z0, because once we have this resistive element, we cannot control the resistive element from here, because that is only JB. That can later on will be able to only control the reactive part. So that will be our first condition, and then from here we can proceed in the same way, and I will just write down the result of this. In this case, we will have X equal to plus minus square root of RL into Z0 minus RL minus XL, and then B will be equal to plus minus square root of Z0 minus RL divided by RL divided by Z0. If there is a mistake, I will write it in the comment section, but this is what I have in my paper. Now, if you notice this thing, we must have, this must be a reactive element JB, and this X must also be, the X and B both must be a real number, which means that the condition that for this to fulfill is that Z0 minus RL must be greater than or equal to 0. So the first thing once you are given a problem is to calculate the value of Z0 minus RL. If Z0 minus RL is greater than 0, only then you proceed with this design. If not, you try the other design. So one or the other design should fit in your requirement depending upon the relative value, the value of RL, which is the deciding factor. Once you have found B and X like this, you can proceed to find the value of the capacitor or the inductor at one particular frequency, and then you can analyze what to do. This L network matching is very well suited if you have a very precise frequency, for example transmitting the power at a very precise given frequency, let's say 113 megahertz or 200-400 megahertz and things like that. I hope this helps you, and I'll keep working on more tutorials and lectures on impedance matching and RF design.